from one person only. Others? Should we wait for a minute or we can start? Hello, am I audible?
Yes, sir.
Should we, so can we start now?
Sure, sir.
Okay. Okay. So, good afternoon, everyone. So, welcome to the fourth lecture on the course Data Structure and Algorithm. We just had a lecture 3 on did operation in 1D array. Now we are a little bit moving on to algorithm analysis part. So in this lecture, we shall briefly talk about the complexity analysis of insertion and deletion algorithm. Then we will move on to the formal discussion on algorithm analysis or complexity analysis. Okay. So let's consider the insertion operation. So I hope all of you have understood well how insertion operation works and its algorithm development. Okay, so we develop the algorithm. Once you develop the algorithm, now focus on the function definition. Uh, as we will see in very soon, while discussing, I mean, formally about complexity analysis, that this portion, this three line, is of no use or will not have any significant contribution towards the complexity of the overall algorithm. The algorithm complexity will be majorly depends on this function definition. Okay, in this algorithm. So what we are interested on, that is finding the number of times a particular statement is being executed. Okay. So for example, every statement, I mean this is your if statement, this is another statement display.
Sir, screen টা দেখা যাচ্ছে।
Okay, no issue. Uh, okay. Now is it's visible? Is it visible now?
হ্যাঁ স্যার, ঠিক আছে, yes
Yes,
sir,
sir.
yes
Yes,
sir,
sir.
yes
Yes,
sir.
sir. ঠিক আছে।
Fine, fine. Okay. Okay. So I hope you have understood the previous lecture, right? Deletion.
Yes, sir. Yes.
Right sir.
Okay, fine. So now we have understood how to write an algorithm. We also understood the explanation of the algorithm. Okay, how to develop algorithm, how to write algorithm, etc. So now once we are able to develop an algorithm for a specific problem, let's analyze the algorithm. How? Let's see. But to analyze the algorithm, what you have to do, your first step is to count the number of times a particular statement is being executed. Okay, so here, what are the statements here? If statement, another statement which is display statement, end if is not considered as a statement which is being executed. Okay, else we may ignore this else part. Okay, for statement, this is an assignment statement. End for is ignored. AI equal to end. This is a statement, and then end else is ignored. So 1, 2, 3, 4, and 5. So total 5 statements are there in this insertion function algorithm. Okay. Now let us try to find the number of times each of these 5 statements which are being executed. Okay. So for first statement is if. So let's write over here. It will be better. Right. So first statement is if. Okay. If statement, and then display statement, and then for statement we need the information. What was that? For I equal to n minus 1 to p plus 1. plus 1. Okay, here I am doing inside it, we are doing right shift ai equal to ai minus 1. Right. Or equal to, we can also write here. N for is not required, we are doing ai equal to n. So, small n. 5 statements are there, right? 1, 2, 3, 4, 5. And then what we are doing, computing the number of steps, number of times this each of these 5 statements are executed. How many times this if statement will be executed? How many times? That is the question. This if statement will be executed only once. কবার এই if statement execute হবে? একবার. If the condition is executed and after execution it will return either true or false. That's all. But it's executed for only one time. So number of count is 1. Number of execution is 1. Next, display. Only one time a message will be displayed. That is also 1. Next, for statement. Now it's important to understand. So how many times this for statement is being executed? For statement means this overall block is being executed. How many times? This overall block, the for block. Okay, that depends on the counter variable, I variable. So I is starting from that we have already
N minus 1.
n minus p minus 1. I equal to I starting from n minus 1 and ending with p plus 1.
P plus 1.
So for all these values of I between, mathematically we express like this: n belongs to the range closed interval n minus 1 to p plus 1. Okay, and where I is an integer. I is an integer. Of course, yes, I integer, positive, negative, whatever. So how many possible values of I we have for which the for block is executed successfully? And that is n minus 1 is greater than p minus p plus 1. So n minus 1 minus p plus 1
This one.
plus 1. Right? So n minus
P minus 1.
p minus 1. So this is the total number of executions of the entire for loop, and these are successful number of executions. Successful number of executions of for loop. Okay, and what will happen when the for loop is completed for the last time, for the last operation, when I was equal to p plus 1. So with I equal to p plus 1, the condition will be satisfied, for loop will be executed, and after that I will be further incremented for the last time. So I will be further incremented from p plus 1 to p plus 2. And then inside, actually what is the first statement in programming? For I equal to n minus 1 semicolon I less than or equal to p plus 1 and then p plus 1 and then I plus plus.
Sir, it will be greater than equal to p plus 1, no?
Yes, yes. Okay, so right, sorry. So this is I minus minus. Okay, so what is happening for the last time? I is equal to p plus 1, and with this value, this condition is satisfied. and that's why the body of the for block will be executed. That is the last successful iteration of the for loop. But after that, I will be further decremented from p plus 1 to p, and that p is greater than or equal to p plus 1. Due to that, the condition becomes false. So for block will not be executed. So for that single unsuccessful execution of the first for statement, that is also one execution. Conditional statement is being executed, p greater than or equal to p plus 1, that becomes false. So that's an unsuccessful execution of only one successful execution of for loop. This thing we have ignored while studying C language, but now in data structure we will consider this extra one unsuccessful execution. Okay, so total number of executions of the for loop hence becomes n minus p minus 1 plus 1. That means n minus p. Next, for for each value of I, for a specific value of I, this ai equal to a minus 1, this assignment operation is occurring only once for each value of I. Okay, or you can say in other way, one for each I, that is so to one for each I. So for all the values of I, you have to sum up one for each I is equal to, what is the starting value, n minus 1, to the ending value p plus 1, and that will ultimately result in n minus p minus 1. Okay, I hope you are getting the point. So
Yes.
this is the difference between the execution of the for statement. Okay, for execution of for statement means what is being executed. I equal to n minus is executed only once. Okay, so these two are executed: conditional statement checking and the implementation or decrementation. Okay, so these two together is executed for n minus p number of times, n minus p minus 1 number of successful executions, and one time unsuccessful execution, resulting in n minus p. Okay,
স্যার বলছি একটু আনসাকসেসফুল এক্সিকিউশনটা একবার বলবেন?
when I equal to p plus 1 for the last iteration of the for statement, the condition is true, but after that I will be equal to I minus 1. When the for loop is about to terminate its operation, this was there, this step, এটা তো জানো,
হ্যাঁ,
রাইট? হ্যাঁ, তাহলে I মাইনাস মাইনাস তো হচ্ছেই ফার্দার,
ইয়েস
সেটা
ইয়েস।
হয়ে কি হবে, I p plus 1 থেকে p হয়ে যাবে। So from p plus 1 I will become equal to p. Then
ও রাইট।
our value of I equal to p will be further used in this condition. Condition will be checked, and while condition checking, it will result in false. That's why further for iteration will not be executed. For will be terminated. That's why. Why
ও
for?
ইয়েস স্যার।
It is the process. So that single execution where for loop condition checking is there, decrementation is there, for statement is executed, right? But it's a false execution, right? I mean unsuccessful execution, and that is only happening
Yes,
only
yes.
once. That extra
Got
one.
it.
So total number of executions of for statement hence becomes n minus p. But whatever statements are written inside the for block, those are getting executed one less as compared to the for statement, right? Whatever
Yes.
statements are present inside the for statement, for block, those will only be executed for all the successful executions of for. Those will not be executed for this one unsuccessful execution of the for loop. Right now, that's why
हाँ,
one less. So n minus p minus 1. And that also can be derived. This can be proved little bit analytically. Okay, so for each value of I, how many times this ai equal to a minus 1 is being executed? ai equal to a minus 1, ai minus 1, sorry, notationটা ai minus 1, suffix এ I minus 1 আছে কিন্তু ঠিক আছে, ai equal to ai minus 1. So this line is being executed only once for a single value of I. So for all the values of I, you have to add up that one. You have to apply summation operator on one. So we are applying summation operator on one for all the values of I equal to n minus 1 to p plus 1. So if you just perform this, it will come to 1 plus 1 plus 1 dot dot dot. How many times? N minus p minus 1 number of terms are there. So a minus p minus 1.
yes,
And that is always 1 less than the total number of executions of for. Okay?
yes, yes, sir.
This is very important. Is it okay now? Everyone understood?
Yes, sir. Yes, sir.
Any doubt, please
Yes,
ask
sir.
me, because this will be frequently used throughout the course. This is very important. This should be very, very clear. এখন ডাউট থাকলে জিজ্ঞেস করো। Okay, it's I think clear. So now this is outside the for loop and a single assignment operator, and it will be occurring only once, no doubt about it. Right? So this is not getting repeatedly executed. So only once it is performed. So now count the total number of executions. So total number of executions, that we will denote as time complexity, denoted by capital T of n, capital T for time, n is the problem instance variable. Okay, for example here, in this case it is capital N. Okay, so it is equal to 1 plus we are adding up 1 plus bracket n minus p, and then plus n minus p minus 1 plus 1. That's all. In the next line we are writing how much it is getting. So I think 2 into, okay, 2n minus 2p minus 2p, and then minus 1 plus 1 get cancelled, plus 2. So this is the thing. And in the next line we can write that 2n plus k. That's all. Where k is equal to 2 minus 2p. And you know, and is a constant. Okay. So here k, the value of k is not variable. Why? Because p is just a single value for the entire operation. P is a value given by the user. It's a position of insertion. So it is not a variable. It is not changing throughout the process. But also you may ask that n is not fixed. Why n is not a variable? It is fixed. But remember, what is n? N is the size of that. And time complexity depends on the amount of data you are handling for insertion operation. If you actually use a large data set, how much time it is taking to perform a single insertion operation on that large data set? So time is the time depending on the size of the data set? Yes. What is the size of the data set? Capital N, amount of data. Okay. And how it is depending on capital N? What mathematical formulation we have derived, that is Tn equal to twice of n plus k. So if we plot this function on a graph, two-dimensional graph, then it will be looking like a straight line. So vertically we are plotting Tn, and horizontally we are plotting n. So it's like if k is non-zero, something will be there, something like this. Please wait a while. Excuse me.
বেল বেজেছে। সাহু।
ক্লাসটা রেকর্ড হচ্ছে, কথা বলিস না।
ও
Okay. Uh, so what we are discussing, right? So graph. So Tn. So if we plot Tn function along vertical axis and capital N along horizontal axis, so from it's a linear polynomial, n is the variable. Okay. So it becomes a straight line where this much amount is your k. Okay. It may be zero. It may not be zero. Okay. So for example, p may be equal to 0. It can be 0 because the minimum value of p is equal to 2. Oh, okay. For p equal to 1, it may get like equal to 0. So it depends. So we are not interested on the exact shape of the straight line. What we are interested on, what we are interested on, what is the growth of the function? So how it is growing up. So versus Tn versus n. What is the dependency? So this is actually linearly growing, following a straight line. That is what we are interested on. Okay, and what is the slope? Slope in this case of 2. So on that basis, it is going on. If slope is more, okay, more steeper, the straight line will be so high growth,
more cheaper.
right? So we are interested on the growth of the function Tn versus n. Okay, so this is actually your time complexity analysis. Only time complexity, space complexity we have not done here. Time complexity analysis. Okay, so we did the same for insertion. We can similarly do the same for deletion operation. So I am not demonstrating here. You try yourself, find the time complexity of the deletion operation, and it will be coming. Okay, I forgot to tell you here one thing. That is okay. So Tn equal to 2n plus k. So we formally write as a big O of capital E. Order of n means what is the polynomial function of Tn? That is 2n plus k. Is it a linear polynomial? Yes, it is a linear polynomial. So any linear polynomial is represented by big O notation of a. We pronounce it as big O of n or order of n simply. Big order of big O of n or order of n. We pronounce it like that. Okay, now coming to formal definition of algorithm complexity. So I will share this lecture notebook. You read thoroughly. I'm skipping the initial part because this is actually the, uh, you know, the evolution of the complexity. So for that purpose, I have prepared some very basic examples, but that what I have done using insertion operation. Okay, coming here. So big O notation. So it's all about a function, time complexity function, right? So now any function like fn, where what is n? N is the variable on which the function is depending on. In most of the cases, n is the number of data present in the data structure. For example, array. In array, how many elements we are handling with? Okay, that is your small n. And based on that, your time complexity is depending on. So what is the time complexity function? So more specifically, we are considering actually the time complexity function. So the time complexity function, for example, fn will be equal to big O notation of some polynomial gn. In our insertion case, it is simply n. It may not be n, it may be n square, it may be 2n plus 3, it may be log n, it may be some e to the power n, something like that. Square root of n, something, any polynomial function. Or any non-polynomial, log n can also be expressed as a polynomial function. any polynomial function, any logarithmic function, okay, any exponential function, etc., etc. So any function, other function is, for example, Gn. So a time complexity function Fn of an algorithm will be equal to big O notation of another function Gn if and only if there exists some positive constants C and N0 such that this condition is fulfilled. That Fn less than equal to C into, this is simply multiplication, C multiplied by Gn. For all the values of n greater than equal to n0. So this C and n0 are the two important parameters. These are positive parameters, positive constants for a specific algorithm. Every algorithm does have their own fixed C value and n0 value. If you can find not fixed, there may be many other possible values of C and n0 in some algorithms. But the major concept is, if you can find some value of C and n0 which are positive, such that this condition is satisfied, then you can say that, conclude that Fn is big O notation of G. Okay, for example, let's say Fn equal to 3n plus 2. In our case, we have 2n plus k. Similarly, some linear time complexity function, so Fn equal to 3n plus 2, and that is equal to big O notation of n. We are saying that Fn equal to big O notation of n. Why? What is the explanation? So can we follow the definition? Yes. How? See. So one technique is, Fn is given as 3n plus 2. So can we say that 3n plus 2 less than equal to 4n? Okay, forcefully we are trying to say that 3n plus 2 less than equal to 4n. Okay, so if we can say that 3n plus 2 less than equal to 4n, then then we can treat this 4 as, see, just compare this expression with this inequality, just compare. This is like your Fn, this is like your C into Gn. Gn is your n. That means it will be your C, and that is a positive constant. 4 is a positive constant. But what about the other thing? Is, can you find some n0 which is greater than 0, positive constant? Okay, so let's forcefully impose this condition. Yes, it is true. Assume that this condition is true. We don't know yet whether this condition is true or not. So forcefully we assume that this condition is true. 3n plus 2 less than equal to 4n, and simplifying the inequality, we are getting n greater than equal to 2. That means now comparing this condition, is n greater than equal to some n0? N0 is positive. N0 positive means the minimum value of n0 will be equal to 1. So is n greater than equal to 1? Yes. In this case, we are getting n greater than equal to 2. So this 2 in this case is acting like n0. So somehow we have found that C equal to 4 and n0 equal to 2, which are positive constants, such that this condition is satisfied. This condition is looking exactly analogous to this condition, Fn less than equal to Cgn. Immediately, we are concluding that yes, Fn will be a big O notation of n. And what are the corresponding values of C and n0? C equal to 4, n0 equal to 2. Just see once, I will take some question or query.
Sir, how will we get the value of C?
It may be 5n, it may be 6n, it is not fixed. See, you try with 5n. Is it possible to get some n greater than equal to n0? Think about it. Do it for 5n.
Yes, sir. In that case, it will be n greater than equals to 1.
1. So it's possible. That is also possible. So I told you that there may be many, these are parameters, C and n0. You can tune them, no issue. So ultimately, our focus is on, are we getting C and n0, which are some positive constant? Some positive constant. Yes, we are finding. That's why we are directly conclude that Fn will be equal to order of n.
So depending on the condition, we will change the parameters.
Right. That may vary from person to person. No issue. That is not a problem. The main focus is main thing is, are you getting some positive constants of C and N0 or not? For all n, for all n. If this is a failure, that has to be mentioned. That means your algorithm is not following this behavior. If n equal to order of n for all the values of n, no, it's not following for all the value of n. So you have to explicitly mention for which values of n this fn is equal to order of n. That also you have to mention. Okay, based on that, there is an example. This fn equal to 10 n square plus 4n plus 2. Now we are doing little bit algebraic method. So we are considering a quadratic based quadratic time complexity function. We just want to verify whether we can say this or not. Does is fn equal to order of n square? We don't know. So let's analyze. So let's try to forcefully impose this assumption that 10n square plus 4n plus 2 is less than equal to 11n square. Will it be valid or not? I don't know. But let's move on. Let's progress further. Assuming that this is true, then next week let's proceed based on this assumption. So assuming that this is true, we are a little bit doing inequality manipulation. What we are finding that see n square is greater than equal to 4n plus 2 after rearranging the terms. Then bringing all the terms in the left hand side, we are doing inequality calculation, algebraic calculation. N square minus 4n minus 2 greater than equal to 0. Then n minus 2 whole square minus 6 greater than equal to 0. And after calculation, what you are getting n minus 2 whole square greater than equal to 6. So we will get n minus 2 greater than equal to plus root 6 less than equal to minus root 6. Minus root 6 can't be considered because n has to be positive. Okay, so we take only this one, this case, n greater than equal to 2 plus 6. Now what is the value of approximate value of 6 root 6? 2 plus root 6, that is more or less 4 point something. It is 2 point something. So 2 plus 2 point something, that is 4 point something. So n greater than equal to 5 we can say. We can't say n greater than equal to 4, but we can say that n greater than equal to 5. So for n equal to 1, 2, 3 and 4, this condition is not true. Means for all the values of n, this condition is not fulfilled. That's what I am saying. For all n. So for some values of n, which is n greater than equal to 5, this condition is fulfilled. This inequality is getting satisfied. So if this inequality is satisfied, and for n equal to greater than equal to 5, so this is acting like your n0. We have found some positive constant of n, that is n greater than equal to 5. So this is your n0 equal to 5. And what is the c? C is this 11. So we got some positive constant c equal to 11, n0 equal to 5, such that this inequality is satisfied. And we have found also that for not for all the values of n, the fn can be said order of n square. For we can't say this statement true for n equal to 1, 2, 3 and 4. We can say only for n greater than equal to 5. So that is the analytical part. Okay, and third point, which through with this I want to conclude this lecture, that is 3n plus 2. Okay, order of 1. Order of n means linear growth of time complexity function. Order of n square means quadratic. It is a quadratic function. So it's a quadratic growth of the time complexity function. What about order of 1? Means it is independent of n. So whatever value of the n is there, the complexity is simply constant. Okay, order of 1. Order of 1 means the time complexity function will be something tn equal to let's say k. K is some constant value. It is not dependent on the n. So it's a computation function is constant computation function. Okay. Okay, so we may have some standard order of complexities like order of 1 is a constant complexity, order of log n, order of n, order of n log n, order of n square, order of n cube, order of 2 to the power n. These are some standard order of complexity notations, which we will see throughout this course. Okay, but there are many other complexity functions available of some complex algorithms. Okay, so with this basic introduction on algorithm analysis, we want to wrap up, conclude today's lecture. In the next lecture onwards, we we want to go more deeper into the topic. Okay,
So you'll give this notes on Moodle.
sure, sure.
Okay.
Any question up to this? You may ask. So let's conclude the class. I'm not